Okay, so in this video, I want to go over a paper by Theodor Estermann from 1937 that essentially proves that almost all even positive integers satisfy Goldbach's conjecture. That is, kind of the fraction of violations to Goldbach's conjecture is asymptotically zero as n gets big enough. Right? And in this video, I really want to go over kind of the intuition behind his main argument, the main idea, and I'm not really going to go into the technical details of all of his kind of hard bounds and things like that. That I may go over in a later video if there's interest. But for now, I just kind of want to go over, give you an intuitive understanding of what his main argument is and why something like this should even be true. Right? And so this is his main result. If you let q of n denote the number of violations, essentially, to Goldbach's problem below some integer n, then q of n grows less slowly than n, as in the fraction q of n over n goes to 0 as n goes to infinity. So this is what he means by almost all, that asymptotically the fraction of violations is 0 for a sufficiently large n. And you can notice that this fraction actually shrinks extremely slowly. It's like log n to some negative integer power. Well, I guess for any negative integer power, but it's sufficient, right? It proves that almost all satisfy Goldbach's conjecture. And one thing I noticed as I was reading through this paper is that essentially his main idea can be very nicely formalized into code. So one thing I'm going to do is kind of plot all these functions that he's talking about and then kind of point at them and try to give you an intuitive understanding of what's going on. You don't have to understand code to follow what I'm doing. I'm just going to basically make some pretty pictures and point at them. But if you do understand code, it may give you a more visceral understanding of exactly kind of what this abstract math is trying to compute. Okay. So with that being said, I'll dive right in, get some boilerplate out of the way. Here we're going to define the integer n. This is the same n that's kind of here as a bound in equation 4 and also in equation 5. And we're going to compute all of the primes that are less than n. And that's to be able to compute this equation 4 here. I want to take a step back and just think about the Goldbach problem in isolation by itself. Right? So how would you compute what's called the number of Goldbach partitions of some positive even integer n? That is the number of ways you can write n as a sum of two primes. Well, kind of the most straightforward way to do it is you just loop through every integer smaller than n, check if it's prime. If it's prime, check if n minus that thing is prime. And if they're both prime, then you add 1 to a sum, and then you kind of keep a running tally, and then you spit it out at the end. So that's essentially what I've implemented here. I've implemented it in kind of a funny way. You'll see exactly why I did that later. I constructed an array called the prime indicator function. Essentially, this is a function that is 1 whenever the index is prime and 0 everywhere else. And what I'm doing for each n is I'm just looping over all indices less than n, and I am checking whether I is prime and whether n minus I is a prime by looking, basically this is a lookup table for primes, and only if both of these values are 1 is the product 1, and then I get a contribution of 1 to the sum. Right? So hopefully it's clear what's going on here, is I'm kind of filtering for primes for I and n minus I, and if they're both prime, then I get a single count, and then I add them all together. And if you go ahead and plot this, you get this nice graph here, which basically just counts the number of Goldbach partitions for every integer n. Right? So the reason I wrote it like this is you may recognize this as what's called a convolution. This is a convolution of the prime indicator function itself. And if you know something called the convolution theorem, you can actually compute this very efficiently using something called the Fourier transform, the fast Fourier transform. And this actually may have been foreshadowed by the fact that I made the prime indicator function array FFT size long. So what we're going to do is try to compute this convolution using the convolution theorem instead. So to do that, the first step is to compute the Fourier transform of the prime indicator function. And so this is what I've plotted here. And even now you can kind of see there's some interesting structure here. So there's this kind of main lobe here at 0, and this is basically just counting the number of primes less than n. But there's also kind of these big negative spikes here, and then there's some smaller spikes in between. This big negative spike, well, actually, this whole thing is periodic with period 1. If you look at the definition of the Fourier transform, because all the primes are integers. So really there's one big negative spike at 0.5 that then repeats with period 1 forever. But this is coming from the prime 2, it turns out. And you can see these kind of smaller spikes here that are roughly 1/3 of the way evenly distributed across the picture. These are coming from the prime 3. And likewise, other spikes are coming from various other small primes. But we're not going to worry about that for now. We're just going to take this kind of as fact. We computed the thing. And then we're going to kind of march on forward and compute this Goldbach partition function using the Fourier transform. And so from the convolution theorem, all you have to do is multiply the Fourier transform by itself, and then take the inverse Fourier transform. And this will give you directly the convolution that we want. And so here I've plotted that inverse Fourier transform as well as our kind of direct calculation. And what you can see is that they kind of align very well, right? Actually, I have two lines, a red one and a blue one, that are kind of on top of each other here. If you kind of zoom back out, you can see that kind of below n, the computation is correct, as you'd expect, and above n, it kind of goes down monotonically to 0. And this is because of the fact that we only took the primes up to n. So really, this is the number of ways to write each integer as the sum of two primes that are less than 1,000 in this case. So you expect as n goes to infinity, kind of you have a correct portion that grows and grows. Right? But it's good to see that this, in fact, does work. And so the kind of the key insight now is that if you want to understand the behavior of this Goldbach sum function, really Goldbach's conjecture is that this function is never 0 at an even integer. If you want to understand it, well, you just have to kind of understand this Fourier transform f times f pretty well. Right? And that's exactly what he's going to do in this paper. He's going to construct a function that's approximately, well, asymptotically as equal to f times f, and then he's going to bound it by something that shrinks as n goes to infinity, and then he can use that to get a bound on the number of zeros of that function. So hopefully that's clear. So how would you actually, approximate f times f at all? Well, the primes are kind of this difficult to understand random thing, right? So kind of the simplest model you can build, if you know something called the prime number theorem, is that an integer n, a very large integer n, is prime with probability 1 over log n. Right? The prime number theorem essentially states that that is true in expectation, that if you kind of integrate it or you add it together, it is exactly true. But we're going to take that literally, right? So we're going to construct a kind of fake approximate prime indicator function by just setting every entry to 1 over log n. What this is saying is that kind of a prime indicator function should be 1 if something is prime and 0 if it's not. So this is saying that's a kind of probability 1 over log n for at every integer n for that n to be prime, kind of independently. And this is kind of the expectation value according to the prime number theorem under any interpretation. I think there's something called the Kramer probabilistic model that formalizes this, and this is essentially the expectation value of that model. Okay, so we have this thing. You can go ahead and take the Fourier transform and compare it with the actual known Fourier transform that we just computed over here. And you go ahead and compute these, and you can see it's not a great fit. That's kind of to be expected because all of these other spikes are coming from the local structure of kind of small primes of 2, 3, and 5, and so on, whereas the probabilistic model doesn't have any of that. It doesn't know that 2 is prime, or that 3 is prime, or that primes can't be divisible by 3, and things like that. But the important feature is that close to 0 is actually a pretty good approximation. And if you think about why that's true, the fact that these two line up at 0 is exactly precisely the statement of the prime number theorem. Because when you're computing the Fourier transform at 0, you're just adding all the terms together. So for the ground truth, it's just actually counting the number of primes less than n, whereas for the approximation, it's kind of integrating 1 over log n, or really summing 1 over log n from 2 to n. And the prime number theorem says that those two things should be asymptotically equal. Right? And in some sense, it's not surprising that it's also true around 0, because all these things are continuous analytic, whatever you want to call it. So on some neighborhood of 0, because it is true at 0 by the prime number theorem, it's kind of true roughly around it as well, right? So that's fine, but objectively, this is a pretty terrible approximation because you're missing all these spikes, and we'll deal with that later. But for now, we're just kind of going to go forward with this kind of crude expectation value probabilistic approximation, and then try to compute what the number of Goldbach partitions should be. So here I'm computing the kind of IFT of g times g. This is an approximation, and here is the actual number of Goldbach partitions. And you can go ahead and compute this. And you can see that, as expected, the ground truth is kind of very spiky and jagged, and we're missing all of that. We basically just get the expectation value. And if you kind of zoom in, you can see basically that our approximation, as you'd expect for this kind of thing, is a very smooth curve that kind of, on average, is correct, but in practice is missing all of this local structure. Right? Even that by itself is actually a pretty cool thing. That we can get the kind of expected number pretty easily like this. But we're missing all these kind of period 2 corrections is kind of the most obvious. There's other corrections as well. And now we want to think about where those corrections are coming from. So kind of the easiest way, or the easiest correction to see is that, at the odd integers, basically the true function is pretty much 0 and the approximation is not. And kind of vice versa for the even integers. The ground truth is higher than the approximation. If you think about why that is, it's because, if you have an even integer and you break it up into the sum of two things, well, half the time they're going to be even. Those can't be primes, except for 2, but we're talking about the asymptotics here, right? And the other half, they're both going to be odd. And a priori, there's no restriction on why those couldn't be prime. Okay. Another thing you might notice, if you look more carefully, is that there's actually a period 3 modulation here as well. So you have kind of a big spike at 330, and then small spikes at the subsequent 2 even integers, and then another big spike here at 336, and then kind of small, small, big, small, small. It's not quite as strong as the period 2 modulation, but it is there. And that also occurs for similar reasons. So if you kind of dive into the analysis, if you have a integer n, which is a multiple of 3, and you think about the possible things that could add up to that, modulo 3, they could be 0, 0, 1, 2, or 2, 1, right? And if you want these to be primes, then clearly 0, 0 can't be the case because, primes cannot be divisible by 3 in, like almost all primes cannot be divisible by 3. So really you have kind of 2/3 that are even remotely possible, right? So 1/3 of them is clearly impossible. But if you look at an n that is 1 mod 3 or 2 mod 3, and you look at the possible summons, they're either 0, 1, 1, 0, or 2, 2. So automatically 2/3 of these cases you have to throw away because one of the divisors is a multiple of 3. And so this kind of restricts your possibilities by a factor of 1/3. And so you can see that you expect the spikes here at 0 mod 3 numbers to be twice as big as the ones at 1 mod 3. And roughly that is indeed what we see. And so this is actually kind of the base explanation for why this period 3 is occurring. And if you extend this to period 2, that also explains the period 2 effect. Right. So what we really want to do is kind of add these period n modulations on top of our approximation. Right. And so there's a few ways to do that, but if you think about it, if you're familiar with something called a root of unity filter, this might start to sound familiar. You want something that's periodic with period n in a very specific way. So if you want to kind of add the contribution for n equals 2, you would want to do something like 1 plus minus 1 to the n, or maybe the negation of that or something. Right? And this is a special case of what's called a root of unity filter. So in this case, for period 2, what we do is we construct the roots of unity, basically the primitive roots of unity of that q. So in this case, if q is 2, this is actually just the minus 1 here. And then you raise all of these to the power of n, and then you add them all together. And this will have a period of q. And the reason is that every time n is a multiple of q, all of these roots of unity will exponentiate to 1. You get constructive interference that kind of gives you a very big spike at every multiple of n. And every time you get a multiple of something that's not a multiple of n, in general, these things will kind of destructively interfere, and you'll get smaller spikes. So for q equals 2, it's actually just basically computing 1 plus minus 1 to the n. You can sum these roots of unity in this way. You actually sum over all roots of unity, all primitive ones, and the way you generate those is you take this base one and you raise it to the power of all coprimes. That's kind of beside the point, that's a detail. But you take what's called all the primitive roots of unity and you raise them to the power of n and you add them together. Right. And if you kind of look at what this function looks like, in the spatial domain multiplied by kind of our continuous approximation here, you get this modulo 2 structure that we wanted. And it turns out that if you add this to what we have here, it will actually basically give you a pretty good approximation of what the ground truth should be. If you look at something like q equals 3, here we have 2 primitive roots of unity, one at kind of 1/3 of the way around the unit circle, and another one 2/3 of the way around the unit circle. So these are the values of 1 and 2 here. You raise them both to the power of n, and you sum them together, and you get something that looks like this. And this is actually exactly the modulation we want. We see that there's a big spike that's exactly twice as big as the small spikes over here, and moreover that the big spike occurs every time n is a multiple of 3. And so if we add something like this to our naive approximation, then it should reproduce kind of the period 3 oscillations that we see. And likewise, you can compute this for other values of q, and you get basically a spike that is, some number of times larger than the other ones, or q minus 1 times larger than the kind of negative contribution from the other stuff. And so you can imagine that if you compute all of these and you scale them correctly and you add them all together, you should be able to approximate the ground truth pretty well. Okay, so you can go ahead and do that. For kind of technical reasons, the way he does this is he defines this function g2, and it computes exactly this, but it does it in the frequency domain. So if you know something called the Fourier shift theorem, this may be familiar. Essentially, we're multiplying by some root of unity to the power of n, right? And so this is kind of twisting the phase of whatever function we put in as a function of n in a smooth manner. And if you go ahead and take the Fourier transform of that, the net effect is to shift the Fourier transform left or right by essentially this 1 over q here, or in general r over q. That kind of makes sense. If you think about it, we're just essentially twisting it by this frequency, and so it should shift all the frequencies by this amount. And so the way that he defines this function g2 is actually to do it in the frequency domain. So here I am shifting the kind of Fourier space representation of g1 times g1 by this fraction over q, and then I'm adding them all together. This is computing exactly the same thing that we computed here. It's computing this periodic modulation, and it's adding it on top of stuff. Right? So now we go back to the kind of Fourier space representation, and we're trying to match all these spikes, right, that we had before for f squared, and we're trying to match them with this kind of g squared like term, possibly with these modulations. So if you only look at the term for 1, that is, we basically just don't have any roots of unity contribution. We have the contribution at 1. This is basically the single spike that we saw before. It's missing all of these fine details. Right? But you can go ahead and add the period 2 modulation. And suddenly you see that we actually reproduce these spikes. Well, there's actually one spike. It's periodic boundary conditions. This one spike that corresponds to the prime 2. And then these smaller spikes correspond to the prime 3. And it turns out you have to scale this by a factor, which turns out to be something related to the totient. It looks like I destroyed something. Oh, I destroyed it here. And you can see that these reproduce kind of these smaller spikes here. And so you can go ahead and add more and more terms here. I really don't want to do that manually. So you can define a function that does that for you. And it turns out that the correct kind of scaling factor to put in here is the Euler totient. That is the number of coprime integers to q squared. One of these factors comes from kind of intuitively interpret as making this an average instead of a sum, because the number of terms here is totient of q. So instead of taking a sum, which blows up as q goes to infinity, you take a mean. And the other one kind of is related to the, it's a little bit hard to explain, but it's related more to the kind of size of the contribution that we expect when we compute this, when we do this analysis modulo q. Right? But you can go ahead and just kind of create this function that automatically sums it for you. If you plug in 1, this is the first partial sum, and we reproduce this single spike that we saw before. If you put in 2, then we get also the contribution from 2. Put in 3, you get this contribution as well. And then in the limit, as you put in enough terms, you should expect to very closely reproduce the true behavior of the f squared function. That is the Fourier transform of the Goldbach, the kind of Goldbach partition count function. And then you can also go ahead and look at this in the real space domain. So here's our kind of first order approximation from before. And you can see that once we add the second order contribution, we reproduce the even odd behavior. That is, we're inserting kind of the modulo 2 information into our Goldbach approximation. We can also insert the modulo 3 information. Now you can see that we reproduce the kind of high, low, low, high, low, low pattern that we saw before that was also present in the ground truth data. And so you expect that as we increase the number of terms here in this approximation, we should start to very closely reproduce the behavior of the true Goldbach count function. And the reason it's not exact, of course, is because n is not infinity. This is really an asymptotic approximation, and that's all that Estermann needs for his bound. Okay, so hopefully that gives you kind of an intuitive understanding of what these functions are doing, why they were defined this way. We're essentially approximating the true prime Fourier transform by this approximate model, and then manually injecting kind of the local structure modulo n. Right? And so basically, the claim of the paper boils down to proving that these two Fourier transforms are very similar, that they're asymptotic. Right? Well, not asymptotic, but that they're bounded by some well-understood function. Right? And so kind of naturally, the way he does this is, this thing by itself is fairly difficult. So what he does is he studies the partial sum, this specific partial sum with some specific bound to this function g3, and instead proves that f squared is close to that. And then he proves that this partial sum is close to the kind of infinite sum. That part should not be surprising. Right, and then at the end, it turns out this is enough to give you the bound that you want. So maybe I'll go into a little bit of detail here. So this is the partial sum up to some bound that he's chosen. What he does is he actually approximates the frequency using a rational number approximation. This is kind of the Dirichlet approximation theorem, if I'm not mistaken. I don't like that he doesn't say the name of the theorem, but that's what it is. And then he kind of splits it into two cases based on where you are kind of in the frequency domain. And then there's a bunch of technical details, but the long story short is that he gets this bound on the true kind of f squared contribution minus this partial sum, right? And he wants to show that it's fairly small. And then for the kind of other half, he uses a different argument and then eventually gets the same result. Right? So once you've shown that f squared is close to the partial sum, all you need to do is show that the partial sum is close to the infinite sum. This part, it's not that surprising because it's a partial sum. So now all I have to do is estimate kind of this L2 norm, L2 difference between the true Fourier transform and the kind of approximate Fourier transform. The reason why he uses the L2 norm here is because the Fourier transform respects L2 norms, and later he wants to convert this into a spatial constraint. So the way he does this actually is kind of crude. He actually just bounds each of these terms separately. He bounds ff squared by n, and then he bounds g by something, and then he just uses the triangle inequality to add them together. There's kind of a lot of room left here, but it actually is surprisingly difficult to improve on this argument. But the thing that actually matters at the end is that he gets his required bound, right? So you can bound this by something. And then all that's left to do after you have this bound is to kind of transform back into the spatial domain. So this is essentially the Planck-Arrels theorem. L squared of Fourier transform is equal to L squared of the spatial terms. F squared, kind of by construction, is in the spatial domain is just the number of representations of m as the sum of two primes that do not exceed our bound that we chose before. And the other term, based on the way it's constructed, it turns out that you can kind of place a bound on these spatial contributions. And in fact, the important part is that it turns out that the spatial contribution for our approximation is actually bounded below by kind of two positive things. Right? So that means that every time that a of m is 0, that is, we have 0 possible Goldbach partitions, this term as a whole has some minimum size. Right? It's bounded below by this thing squared. And so the kind of contradiction that you get is that if you have too many places where a of m is equal to 0, then you have too many kind of terms that are bounded below by some quantity, in fact so many, that it violates the bound that we have on this kind of Fourier space L2 norm. Right? And so that's kind of his argument here, is that basically this, if a of m is 0 too many times, is bounded by the number of terms that are 0 times this, and if you enforce that this must be less than the bound that you derived before, you can get an upper bound on the number of zeros, essentially, in your kind of a of m function, the ground truth function. That is the Fourier transform of f squared. Right? And so this is kind of how he finishes off. So all you need to do is basically make sure that these two functions are close enough together and make sure that G3 contribution is never 0 by itself, and then you can kind of argue that a of m cannot be 0 too many times, otherwise you would get a contradiction. So, in some way, more or less, that's the whole idea of the paper. If there's interest in a future video, I might go through all the details of how he bounds this kind of stuff. It's all just kind of technical, right? But hopefully you got some idea of the kind of main argument that he's trying to go to, as well as some intuition for why it's true. And as before, if I remember, I will kind of link this notebook or something like it in the description so you can play around with it for yourself. Let me know if you're interested in kind of seeing the technical details. I may make another video, or if there's other papers that you want to see. But again, this kind of was mainly for the benefit of my own understanding, kind of giving me motivation to code it up like this. But hopefully some people found it interesting. And that's all for now. Take care.